No, ma'am, you are not audible. Ma'am, your slides are visible, but your voice is not coming.
Good morning, Dr. Ankita. Hello, am I audible to everyone?
Yes, sir, you are audible.
Yeah.
Yes, sir, you are audible.
Yeah. Okay. Thank you. Dr. Ankita, I think you may try restarting your system.
Hello. Am I audible here?
Yes, you are audible.
Yes, I
Yeah.
will connect the audio from my phone and I'll just start the PPT.
Okay,
Till the
okay,
time,
sure.
yeah, the system person arrives.
Okay.
We'll not wait for him.
Yeah,
Okay,
thank you.
just give me 2 minutes. We'll start.
Yeah, sure.
Hello.
Good morning, ma'am.
Good morning. Yes, extremely sorry for the technical delay. This was not expected, but we'll start immediately start with the PPT.
Um, First, I will just to introduce you first.
Okay, okay, sure.
Okay. Good morning to all participants, speakers, and faculties. We are honored to have Dr. Ankita Harkare ma'am from Sri Ramdev Baba College of Engineering and Management, Nagpur, for this session. First, let me introduce to Dr. Ankita Harkare ma'am. Dr. Ankita Harkare work as assistant professor in Department of Electronics and Communication Engineering at Sri Ramdev Baba College of Engineering and Management, Nagpur. She has worked as system engineer at Tata Consultancy Service Private Limited, Pune. She has joined teaching profession for her passion of teaching and research and has 7+ years of teaching experience in the domain of electronics and communication engineering. She has 10 plus research paper to her credit. She currently has 2 patents published and has successfully completed consultancy services in her domain too. Her current research interests are antenna and MEMS. Once again, we welcome you, ma'am, and thank you so much for accepting our invitation. Over to you, ma'am.
Thank you so much, and I'm again extremely sorry for the delay. Uh, so, thank you for the overwhelming introduction that you have given me. So, we'll not waste any much time. We'll start with the topic. So, in this session, I'll be discussing machine learning based optimization in dielectric resonator antennas. So, though we are discussing the machine learning based optimization, it is advisable or it is expected that we know our antenna very well. It is not that we will do everything with machine learning. The optimization part, wherever we apply parametric analysis, all are mostly the antenna engineers here. So will be knowing that there we can have the machine learning based optimization, or if we are using in techniques like switching or something, there also we can have machine learning optimization. So just a brief introduction about my college. So as rightly said, uh, I am from Sri Ramdev Baba College of Engineering and Management. In short, we called it RCOEM. It is in Nagpur. But now we have transformed to private university, and we call it Ramdev Baba University RBU. So if you happen to be from the central region here, you can you must be knowing this college because it is after NIT Nagpur. This is the preference of all the students. So this college is now private university. So just to start with dielectric resonator antennas, most of you know about it. So why we are actually going for a dielectric resonator antenna? Apart, though we are already having dipole monopole patch antennas available and already commercially being utilized, but still DRAs are much talked about. And if you can see latest transactions in IEEE, they are concentrating on DRA. Why this DRA is coming into play? Basically, we are having a ceramic material here. So the metal part here is mostly only the feed and the ground plane, of course. The antenna part is a ceramic material. Now, since it is a ceramic material, it will have lower ohmic losses at higher frequency because it is more temperature stable. So weather conditions will also not affect it much. The At higher frequencies, that are the current domain, that is terahertz, we are talking about millimeter wave frequencies. Dielectric resonator antennas are actually having a very promising future. So just a short uh, history. Though the theory started way back in 1939 or so, but the actual analysis started in the 1980s by Stuart Long and Liang Shen. They studied different type of antennas. They have published papers also in that, and those papers are like a bible for any person who is working in dielectric resonator antennas. So different type of shapes can be uh, when we can have, it is not limited to this cylindrical, rectangular, hemispherical. I have put here because these actually give us the theory behind the waveguide. The waveguide theory, which is related to the antenna, and we do the analysis. So these are the basic shapes for that. Then different types of feed were also analyzed, and we can have different bandwidth gain polarization using DRS. So in the work that I'm going to discuss here, it's mostly for C band and X band. The C band frequencies that we mostly talk about are 4 to 6 gigahertz, that is sub 6 gigahertz frequencies for 5G. And for 6G, most of us have this tendency to talk about terahertz frequencies. But we forget that we are having a band from this 6 to 10 gigahertz, which is actually not having any, it is not licensed till now. But if you see the papers and you see the results or the discussion in communication or service providers congress, like this data has been taken from gsma.com, they are proposing to extend this frequency, and our area of interest is mostly for building management systems, that is inside the building. That is, we are talking about this IoT and IoB, internet of building, internet of things. So that was the main concern. So we started our journey beyond the sub 6 gigahertz frequencies. So the types of antenna we, as already discussed, are rectangular, cylindrical, hemispherical. From this, we are actually concentrating on the rectangular DRA. So why the rectangular DRA? The main reason was to have this 2 degree of freedom. The 2 degree of freedom, as in I am having the length and width both for in my like I can vary this, and different sizes can be explored. In cylindrical, the air gap issues as observed are more, and we do not want that. So we have not selected cylindrical DRA for our study. And hemispherical are also having lesser air gap issues, but the analysis with respect to basal functions and everything, that gets tricky when you modify the design, not the basic design. The basic design is, we know the theory about it, but when you modify the design, you need to have a theory behind it. You cannot just have any cuts anywhere. So that is why we had selected the rectangular DRA for our research domain. As already discussed, these are the some advantages that we receive. We can have wide bandwidth and low or no conduction loss, high efficiency, broadband nature, and they do not suffer from surface waves, and we have a degree of freedom. But the main challenge that lies is that here is the frequency, if we see, is inversely proportional to the dielectric constant as well as the size. Now, because of this, if we can have the relation here, if we have the relation here for a higher frequency, we require a lower dielectric constant. And for the size, for the minimums, if we want a minimum size, we want a higher dielectric constant. Now this becomes a challenge because we are mostly designing dielectric resonator antennas for higher frequency and not for the lower frequencies. So this is actually a challenge for us. So you have to have a trade-off. Now the advantage of dielectric resonator antennas will actually, we will be able to see when we use a higher dielectric constant material. If we use a lower dielectric constant material, then the analysis wise, if we calculate the reflection coefficient, it will not be nearer to 1. When we are calculating the reflection coefficient for a dielectric resonator antenna and air being one of the, like, if this is a dielectric resonator antenna and we are having a boundary condition, so when we calculate between air and dielectric resonator antenna using the formula, we will get better results when epsilon r is approaching infinity. That is what our theory says. So this means that we want an epsilon r of a higher value. But then if you have an epsilon r of higher value, your frequency will decrease. Then there is no purpose for discussion because we are mainly discussing dielectric resonator antennas for higher frequencies. So these are some of the DRA design equations. It is similar to our rectangular waveguide. The wave numbers are calculated. Here A, B, and D are uh, length, width, and height. So we can have D constant and we can calculate A and B, or otherwise we can have A constant and we can calculate B and D for a particular frequency. Depending on the size or the fit that you want, you can do that. So in our design, we designed a wideband circularly polarized antenna for C and X band. Now the circular polarization came into picture because we are actually concentrating on the in building communication. Now, when we are having a communication inside a building, the problem is the concrete walls and the structures. We can observe it very clearly when we are passing through very tall buildings. Our signal gets distorted because there are a lot of losses because of the concrete structure. Now, this needs to be reduced. Now, for that, of course, polarization, if we have a circular polarization, we will be able to have our proper signal strength and we will be able to do the communication inside a building. So one of the method that we are using for circular polarization is the orthogonal feed. Then for better gain, we are using stacking and air gap. We are introducing for bandwidth enhancement, and we will have a second design that will actually show how the circular polarization just increases by almost 50%. These are some of the techniques of gain enhancement. Here we will also discuss FSS, which is after the design. I will also introduce FSS in the design. But before understanding the design, if I directly go to the FSS structure, in the design, probably a lot of you might not be able to understand. So these are some of the graphs that is also there in the paper Evolution of Gain Enhancement Techniques in DRA. So we have there discussed how FSS technique is also one of the technique for increasing the gain. And higher order modes is also one of the technique of increasing the gain. But the problem with higher order modes is after a certain point, we cannot just keep on increasing the modes. We can just not go from 180, 11 to a lot of higher modes because there will be when higher order modes are involved, the power losses are also high. So that technique has its limitation. So after a certain point, when you have a gain increment, you can use definitely. So I would like to bring your notice to this technique here. Now, this is the evolution of the design. Now here, this is a basic DRA. This one, the first one, antenna 1 is the basic DRA. This is the top view and it is fed by orthogonal feeds. Now why the orthogonal feed? Because if the feed is like this, the direction of the E fields will be like this. Now if I'm feeding it in two direction, so it will be like this and then some of the fields will be turning like this. So this will actually have an effect of a circularly polarized uh, signal. So that is why orthogonal feeds were used here. Now from the side view or the front view, if you see, this is my DRA. Here you can see this conformal feed. So we are also adding a conformal strip. The pictures I'll show it in next slides. Conformal feed, as in if this is the DRA, I will have a metal strip here. Now this has an effect similar to our coaxial probe, coaxial feeding. And the disadvantage of coaxial probe is that when we have a hole for the feed there, the air gap are introduced. So those air gaps are not in our control. But these air gaps that here we are introducing, this perforation, that is in our control. So this needs to be minimized. That is why instead of coaxial cable, we are using microstrip feed and along with that conformal strips. So this is the first view that is done using a simple DRA without anything, only the simple DRA. The material that we are using is alumina, having a dielectric constant of 9.8. Now in the second antenna, there are these perforations that are added. The perforations are, these are the perforations. Now, if again I will try to discuss it, if you just divide the antenna in the DRA in three parts. So these perforations are for the each antenna. Now, why we are doing this? Now, if I have designed the first DRA for 6 gigahertz, antenna 1. Now, if I want multi-band functionality, so this was not being we were not able to achieve it properly with the single DRA here. So we divided it into three parts. We calculated the frequency. This each DRA is giving a frequency of 3 gigahertz. So we should be expecting a frequency of 6, around 9, and around 12 in with each this block. And also one thing that needs to be taken into consideration: these perforations are not through and through. Before our design, a lot of papers have been published for DRA with through and through design. That is, this the perforation, the holes were throughout the antenna. So if you see the side view of the DRA, the holes will be throughout the antenna from the top to the bottom. But these are not through and through. Now, just I would like to bring your notice from antenna 2 to antenna 3. What we did, we divided this antenna into two parts. Means we split this antenna from half, from the point of this conformal strip. And we introduce a air gap in between. So the same antenna, the 6 gigahertz designed antenna, we were splitting it into two parts. And we introduce an air gap in between. It was not any parasite, or it was not any other parasitic type of slab or anything. There are papers where another slab as a parasite was kept above the DRA for increasing its bandwidth, but here that was not the case. The same antenna we have used and introduced an air gap in between. So this air gap that we are introducing, that is in between the antenna and not apart from the design. So because of this, the compactness of the design has increased. So this is a very compact design. The aspect ratio is 1.65 or so. We till now the papers are not but we are seeing it. It is not nearer to 1.8 or so. I have seen it, but 1.65 and below that. So the entire dimensions are very compact because of this theory behind it. And the last part, excuse me, that I am utilizing the DGS here, that is defected ground structure, for enhancement of axial ratio. That will be discussed in further slides. So here this is just a comparison of antenna 1, antenna 2, 3 and 4. Here this 1, 2, 3 and 4. So you can see that percentage axial ratio bandwidth that was observed in the first case was 15. Then the impedance bandwidth was around 10%. Gain was around 4.2% at 6.3 gigahertz. Now the shift in the frequency will be there because at each stage we are introducing some air gap in between, and the air gap that is introduced by even by sticking the DRA on the microstrip feed, that also introduces the air gap, and there are certain fabrication issues. So that because of that, the 6 gigahertz frequency has shifted to 6.3 gigahertz of frequency. So, and the parameters proposed design, as I was talking about, of the DRA is 15 mm by 15 mm. The whole dimension, the complete dimension is fitting in 30 type of a structure. Now here, why the perforations were introduced, or why there was a hole that we introduced in the DRA, that is explained. The holes, what they are doing, when I'm introducing a hole on a DRA, there is an introduction of air gap here also, and I'm removing the dielectric part from here. So when I'm reducing or removing the dielectric part and I'm introducing a air gap, and also I'm introducing a air gap here in between the two parts of this design, my effective dielectric constant has changed. Now this effective dielectric constant depends on the center to center spacing between the holes, the center to center spacing, which is 3 mm, and also the diameter of the each hole is also 3 mm. Based on that, if we calculate the effective dielectric constant, that comes out to be, it's around 6.8. So the ceramic material that we used was of 9.8, that is alumina, but we are reducing this to 6.8. Now this is a trade-off for our challenge, that is F is also inversely proportional to epsilon r, and size is also inversely proportional to under root of epsilon r. So here we need to have that trade-off. We cannot have a dielectric material lesser than alumina, or even the Rogers material, which is around 11.2 dielectric constant, but we can definitely have an effective dielectric constant lesser than what is expected, so that we can have a compact design and also we can increase the frequency. So these are the E fields. So from the E fields, if you can see, we have by introducing the perforations, we are introducing higher order modes in the DRA. So initially, it was acting with the T10 mode or T11 mode design, but then with the help of the perforations and the air gap, we are introducing higher order modes. Now this needs to be restricted somewhere. So the design, if you can see, this was a single block. This was a single block first, and then air gap was introduced. It was split into two. Air gap was introduced. Now this is a foam which we are using as an air gap because the dielectric constant of foam is 1.2, so which is very nearer to air. Rather than using screws, if you use screws or if you use any adhesive material, the dielectric constant will again increase, and then the design will not be. Then in simulations also we need to add those things. One thing that we need to keep in mind while designing a DRA is whatever material that we will be using later on for assembling this. Like if we are using an adhesive material here, we are using an air gap here. We need to know what materials and what technique we will be using to stick that or to assemble that. Like if we are using screws here, then what type of screws will be there? Whether it will be of some polymer or whether it will be of some metal or anything. Then accordingly, our simulation results should also state that, and then only we will be able to get the simulated and measured result properly. It will then only they will agree properly. Otherwise, then the designing is of a DRA without, we will put air as a simulator in the simulation, then we will not get any results similar to what we are expecting. Yes, so discussing the DGS, so why we are having this DGS here, these along this side, because we needed to have the surface current concentrate at the center here. When we have the surface current at the center, they will be able to excite the DRA properly. Now, all these things, this parametric analysis have been performed to get the number of slots, the length of, and the length and width of this uh, size of this DGS. The parametric analysis was performed here. Now, these parametric analysis will be very important for our ML design. As I already said, For the DRA structure, we are not using the ML because the mathematics is already available for it. How we will be the structure, design, and everything, the mathematics is available for it. But for the parametric analysis or for the increasing the or enhancing any parameters here I have performed parametric analysis. So definitely this data will be used. I can use ML here. I can modify this design and I can make my task easier rather than performing parametric analysis. I can have, if I train my model properly, excuse me, I will be able to get the results very in few seconds rather than wasting a lot of time. I'll not say wasting a time, but rather than doing a lot of parametric analysis, here we can have that. So this is the place where ML can be or machine learning algorithm, learning algorithm can be useful and integrated in antenna design. So this was the result of our first design. What we were able to achieve a gain of around 5.5 for the basic center frequency, and throughout the bandwidth, uh, it was above around 3, about 3.2, above 3.2. The gain was about 3.2. The axial ratio was maintained. So the axial ratio bandwidth was 38% and the 10 dB bandwidth was uh, 39%. So almost like complete overlap of axial ratio frequency. I hope I'm audible. Can we continue? Any
Yes.
doubts?
No, continue.
Okay. So this was the first design. Now, if this was understood properly, uh, next task was to increase this bandwidth as well as both the bandwidths, the impedance bandwidth and the axial ratio bandwidth. If we can increase that beyond 38%. So that was the next task without disturbing too much or without disturbing the DRA part if we are able to achieve it. See, DRA is, they are definitely having the advantages, but the problem is still the fabrication part and fetching the material still is a difficulty. So if we are able to keep the DRA design constant and play with the DGS part, that also is can be considered. So when you are having a basic design ready with you and we are able to modify it slightly and get the improved results, that is also what a designer should think in that perspective. So this the next design, just observe this design. What we have done from the previous design. The upper part, the upper portion disc, this I have rotated with a angle. Rest all the things are constant. And of course, there is a different type of DGS. The reason I will explain why we are using this. So only the upper disc is rotated by this angle. Here, this angle rotation was introduced to introduce orthogonal modes in the structure. When the orthogonal modes are introduced, your CP will increase. So CP increases, but what about the bandwidth? Now to increase the bandwidth, the same DGS structure that we were using in this technique was not it was not sufficient. So this dumbbell shaped structure was introduced because it will have a kind of a LC filter type of a equivalent circuit. So we are actually increasing our bandwidth using this dumbbell shape. Now this dumbbell shape, the length and width, we are able to do it according to the requirement of the frequency that we want, the increment in the frequency. But that this distance of this dumbbell from the ground plane, this is in our hand. This is the parametric analysis that we can have. This is fixed, but here the distance is in our hands. Also, this structure, the cuts here, DGS we are calling it, and the distance we are calling it DBM. This is one of the parametric analysis that can be performed for our ML. In further slides, we will see that. So again, the same comparisons, and the comparisons with respect to angle was also performed. So 45 degrees was actually giving us proper S11 and axial ratio. Every time when we are performing the parametric analysis, we need to fix our goal that we want a high bandwidth more than 38% that we achieved in the previous case, and also we want the axial ratio that is proper, and it is beyond what we have already achieved. So that is in every case that needs to be kept in mind. So here you can see those surface the e fields from the top view, where we can see that how the circularly polarized waves are present inside the top view, and it is contributing to the total AR bandwidth of the structure. So these are the E fields inside the DRA. Again, you can see that higher order modes are introduced here for different phases, or you can say for different times. So simulated and measured results were also agreeing, and we were able to get the highest gain of 8.7 in this case. So mainly the reason of rotation and introducing that dumbbell, which is introducing a LC type of a circuit or equivalent circuit inside the DRA, we are able to enhance the bandwidth and also the gain. Is not enhanced because of the rotation. It is definitely enhanced by introduction of higher order modes. But higher order modes are also introduced because of the rotation part. So now, from the previous design, we were able to get almost like 72% of bandwidth here, which was 38 to 39% in the previous case. So perforations, rotation, and DGS technique. Three techniques were introduced in this. DGS was also introduced in the previous case, but we are not using that slotted type of DGS just for the surface current. Here we are introducing that DGS for having a filter type of effect, or a band stop filter or band pass type of a filter here. Now coming to the optimization using ML algorithm. So as I already told you that the DRA part we are keeping constant, but the DGS part we can play with, or the defected ground surface we can play with. Similarly, when we are going for FSS structure, that I'll explain in the coming slides, there also we can have ML based on the distance of the FSS from the DRA or the placement. There we can have the ML algorithm. So what ML algorithm is actually doing, where we can do it. So for example, here I have taken length and width of the DRA. If you want to vary the length and width of the DRA, so that will be my feature. And I am predicting the frequency based on these variations. So if I am having a band of 6 to 12, 6 to 12, and if I am having a center frequency, suppose around 12, around 8. So I will have this entire data sets from any software that you're using, CST or HFSS. Now, one thing that a lot of us get confused is what exactly ML is doing here. So machine learning algorithm will always come after the design. This needs to be very, very clear in our minds. So the design modification that I'm doing, like for example, the previous design, if I show you, I will keep the base model constant. And now as per the requirement of, suppose if I am having any requirement that I do not want the bandwidth of 72 degrees, I want 72%, sorry. So I want a bandwidth of only 50%, and I want my center frequency of around not 6.5, I want it around 7. So I will not change the base model. This base model will remain as it is. But I can definitely modify this bandwidth based on the DGS technique, that is the defected ground technique. So the defected ground structure that we have discussed right now, this one. The dumbbell will remain constant, but the distance of this dumbbell can be varied, and of course this cuts can be varied to get a desired result. So ML will have a we will have a verification. Right now we will just verify. So first we will be having a verification. So what we are verifying? We are verifying that whether the ML model that we are introducing gives us the S11 exactly as what we are already getting in the simulated. That will be the verification based on different type of parameters that we will be checking. So that first we need to verify. So first as the model is verified, then only we will be able to have a prediction. You cannot directly predict it. I cannot directly just go on and predict the model. No, first we will need to verify whether which model is suiting for our problem statement. We will verify, we will get the results, and then we can have design a predictive model based on certain features, not all the features. Whatever features are mathematically analyzed already, which are having the theory behind it, we will not touch those. We will be doing the analysis only on those parameters which are actually we have also used as an antenna designer. We have used parametric analysis for enhancing its features. So I will not touch the length and width of the DRA. I will not touch uh, the exact geometry of the DRA. I will not touch the microstrip feed line calculations because those are well tested, having a mathematical analysis behind it, why we are using that much length and that much width of our microstrip feed. But we can definitely do that on DGS. We can also do that on the rotation angle based on the requirement. So these are the things we need to keep in mind. Now, first thing that we will do is we will verify it. We will verify whatever I am getting till now, simulated measured results are agreeing completely. But and the mathematics behind is also agreeing completely. But is the ML algorithm will agree to whatever we are getting? So that is what first thing is verification, and then the prediction will come into picture. So this is the same model, the last one, the rotation one that I have shown you. The ML has been applied on that model, not the first one. So please ignore this red line because that is a measured result. We all know the measured result will not be exact as compared with the simulated results. So the what we will get, the ML part will be, it will be nearer to the simulated or the CST results that we are getting. So here the algorithms that we are using, the regression algorithms mostly that we are using is DT. DT is nothing but decision tree. RF is random forest. KNN is K nearest neighbor, gradient boosting, and XG boosting. Now, just as a brief, because I understand that a lot of us do not understand this, but I'll just give a briefing of what these algorithms actually mean so that next time whenever if we are thinking to apply ML, we just know the basics. We know the basics that where this will fit. Also, I will like to give a caution that a lot of new algorithms are coming into play. Now, these algorithms are not necessarily what is my observation and with the work that we are doing and my students, the algorithms that are actually very famous, like gradient boosting, XD boosting, these are very famous algorithms, but these are not working on antennas. These are not giving us best results. We will have to understand that antenna design is complicated, and for an ML algorithm to understand it completely, we need to also understand our design properly. Then only it will give us a proper result. So just as a brief, I want to give you, probably a lot of you might be knowing it also. Decision tree is like a decision. Like if I am having a center frequency of 6 gigahertz, I will have S11 below -10. If not, then I will not have. So this is like kind of a decision. Now these decisions need to be elaborated, or it needs to have more decisions inside it. We cannot have just a single decision for our antenna. So decision tree is one of the method. Next method is RF, that is random forest. Random forest is actually collecting the entire. It is like a collection of decisions. It will, or you can call it, a lot of people call it collective intelligence. So random forest is like a collective intelligence it will give you for your design. It will just not do the decisions based on this is decision yes, no, no. It is not like that. It will have a collective decision. Okay, whether in next conditions it is satisfying or not. So that is what is random forest. KNN nearest neighbor. KNN is nearest neighbors. K nearest neighbors means what? If this is my point, suppose. So I will have K can be anything. You can choose it. K can be 0, 1, 2. If I take it 0, there is no point. Either you can start with 1, or here we have taken 3. So I will have the 3 nearest neighbors of this point. And I will try to predict it then, whether this point is working fine or not. Now KNN is having a problem with our designs. It will not work properly for S11. It's such a complicated type of circuit. Just imagine I'm having a 3 nearest neighbor for this point, and immediately the next point, if this is the next point, again I'm having 3 nearest neighbors here. So the model itself will get confused whether to take the already existing point or the other points as a k nearest neighbors. So a complicated type of a curve will be a problematic for a KNN. Here, where the gain and axial ratio calculation, where we are having the points, just we need to mark certain points and not have a curve. There, probably KNN will work better. The KNN work, if you see the literature, it is mostly used in stock exchanges and everything. Then, uh, if we talk to some ML engineer or a person who is working in this field, they will be an advocate for gradient boosting. So why what gradient boosting is doing? It is minimizing the gradient errors. But again, if you see the values here, in our case, it is not proper. Why? Because the disadvantage of gradient boosting or any type of a gradient boost like SD boost also, they will fail when a lot of noise is there in the system. Now, in our case, for I'm just talking about S11 curve, now gradient boosting will consider a lot of points as noise. So either it will have underfitting type of a curve or it will have an overfitting type of a curve. This is a problem here. Otherwise, in any other type of situation, suppose if you are taking a graph of your salary versus your increment, yearly increment, the increments. So this is a normal type of a scenario which will not have very much variations. So for those type of a scenarios, gradient boostings and XG boost will work. Of course, I'm not denying the fact that any person can have can bring a lot of changes in the algorithm and just enhance that. But currently, with the current scenario, that what we have observed with the basics of ML, these algorithms are not working fine. Rather, random forest is giving us the best results for the cases that we have studied till now. For our design, specifically, I'll say for my design. For other designs, these may vary. So again, whenever we are applying, I'm repeating this, whenever we are applying ML for our design, first thing is that we should understand our design as an antenna engineer. We cannot just keep on having a ML without understanding our design. Okay. Another thing is which parameters to take. Like here, if you can see, I have taken MSc, MAE, R2 score. What are these? I hope I am confident a lot of us might be knowing this, but still, again, just those who are not knowing, I'll try to explain it in a very easy manner because the thing is, we need to, as an antenna designers, we need to change with the and we need to accept the changes. But all these factors are simple, they are simple, but we are probably not knowing it. So we don't understand why these things are important for us in our antenna design. So I'll just explain it in short. It's nothing to, I'll not take much time here. So what is MAE? It's mean absolute error. MSE is mean square error. And R2 score is like a score which varies from 0 to 1. And nearer to 1 means our model is proper. If it goes negative, then definitely you should discard that model. 0 to 1 is the range. So nearer to 1 means we can accept that model in our design. So what is a mean absolute error? So I will just explain it with respect to linearity. Though our in antennas we are not having anything linear. So if suppose these are some points, and this is a regression line, right? So with respect to this line, if I am considering this point, so what is the distance of this line with respect to our y-axis? This much. Let me name it as y1. And what is the distance of this point with respect to the regression line? Let me call it as y1 dash. So the difference between the mod of difference between y1 and y1 dash is nothing but our mean absolute error. It is the absolute error. So this mod of, if I say y1 dash minus y1 or y1 minus y1 dash also, since it is mod, I'm not concentrating much on it. This value should be as minimum as possible. That will tell you that whether the regression line that has been drawn by the algorithm, this line, is how precise that line is. And when we are talking about mean square error, means if this is a point, I'm not considering the same point, means the distance from our regression line and the square of it, the entire square that we are considering. That is a square thing. The problem with MSC, that is mean square error, is that it is difficult to understand. The values are all given in square. It is square of everything. So we are unable to understand it properly. So that is the thing. So RMSE comes into picture. RMSE is root mean square error. So this value is acceptable. We will be if any value you are given S11 value, you are being given as a square. Means I am expecting a minus 15 dB. I get a square of that. So I'll not understand. A root mean square error is a simpler version of it and a precise result. And this is very important with respect to deep learning algorithm, RMSC. Here I am just applying ML so that everyone can understand. What is R2 score? Now R2 score, again, if I take I go to the previous slide. Here. So what is R2 score? Again, if I'm having some random points, I'll have a mean line. This is my mean line. And here, this is the regression line. What is a regression line basically, if people are asking? It is a line or it is, I'm again explaining with, let me clarify. It is only with respect to linear regression that I'm explaining it to you. But in our case, we are not applying linear regression. It is not possible in antenna design to apply linear regression. Just for explanation, I'm using linear regression. So what is a regression line? It is a line that is actually passes through most of the points or in the vicinity that you can understand. That is a regression line. And this is a mean line. So this, if I'm considering this point, this one, let me call it as point number 1. So its distance from the mean line and its distance from the regression line. So that is 1 minus the distance of it from the regression line. So again, if I call it as x1, sorry, y1 and y1 dash. So distance from the regression line upon distance from the mean line. So if we read it or we try to analyze what it exactly means, it is 1 minus the best case scenario, which is a regression line. This is a best case scenario, and upon the worst case scenario, that is a mean line. So that is what exactly the meaning is. So nearer to 1, if I get my R2 score or R square or R2 score, we call it, means our model is almost nearer to perfect. So this difference, best case and worst case, should be as minimum as possible. That is what the R2 score actually means. So again, just see the S11 scores. So DT, RF, KNN, XG boost, all are nearer to 1. But again, go to the AR, that AR axial ratio comparison model. If you see, all these values are not nearer to 1. RF is 0.6, KNN is 0.5, means there are a lot of scope of improvement here. So what is happening here? What is our observation here is the data sets or the data points that we have used to train the model for S11 is around 1.5 lakhs. Any model that we are training is not less than 1.5 lakhs, then only you will get the precise result. That is what these values are actually telling. For S11, that is possible. But those who have worked in CST or any other software also, they know for these values reduced by half. Because for the gain and for axial ratio, I do not need to plot a curve. I don't need a curve. Wherever I need a curve, it is possible for me to have high data sets. High data set, I'll be able to get around 1.5 lakhs or so. Data sets points I'm talking about. So for plotting this, for training this model, I use 1.5 lakhs, and for testing around another 20,000, 30,000 points we have used. So you need to divide your data into training and testing. That also needs to be clarified. But for gain and axial ratio, we are not able to achieve data sets beyond 15,000 or 20,000. So of course, my R2 score, MSc, all these values will be bad because I'm not having that much amount of data sets. So for the observation is for bandwidth related issues, ML definitely will give you very closer result. These all curves have been plotted with respect to the algorithms, but axial ratio will get certain points. Gain, we did not do it. We did only for axial ratio because for this problem statement, we were concentrating more on the circular polarization part. So that needs to be kept in mind. Just randomly saying I'll apply ML, it will not work. First, understand your data. Whatever you are at, that is why to understand the data in antenna design, you need to understand the design. One fine day, anybody can come and say I'll design an antenna using ML algorithm without knowing your design or without knowing the problem statement. This will become very difficult. So that is again and again a reminder, because a lot of students are now directly coming. Even my students, they want to just apply ML, but without having a perfect understanding of the design, or without understanding what exactly the design is working upon, how the e-fields are working, where you need to have a cut. Anywhere randomly you cannot have a cut. Where you need to have a cut, where your design with that cut will help your design grow rather than ruining whatever you have got till now. That understanding is required. I'm just giving this as a reminder and a caution again and again, because this is what my observation is. Once I say that we will be applying ML, students just, or research scholars, they just want to do ML without understanding the design. So this is a word of caution here. Without understanding the antenna and its working, please do not go for ML. ML is for enhancing our results, right? So these are again the results based on different algorithms that we have done. again, I've already told, I think so. The best results that we are observing is with respect to, I think, random forest. Random forest is giving me the best fitted curve. Best fitted curve means the curve that is nearer to the simulated results that we have got already. We have got. So this is the verification part. So I have verified now that this design, this single DRA design, is working well with random forest. Now, how I will predict it? Now, next comes, okay, I have now verified. Let us try and predict it. So what we did is we predicted it with a MIMO design, the similar type of a structure with MIMO. So we first, now here we tried and played a little, because the structure now we know exactly. This DRA structure we understand. We are not taking it randomly. So before going for the fabrication, we first did it with respect to ML. We had this, we did it for 4x4 MIMO single and 2x2. So this is a just a comparison of 2x2 MIMO single and 4x2. And later on we fabricated it. Of course, I changed the DGS later on. It's not the same DGS, but later on we fabricated and we found that the fabricated and measured results are similar to what we have observed in ML. Not exactly, I'll just claim 70%. 70% they are similar to what we have observed. So what we did, if we see the flow, first we understood the design, we verified it with already measured and simulated results, and then we tried to predict a MIMO design using the same structure, right? So we predicted it, and when we measured it, it was similar to what exactly we were trying to do. So here ML can be utilized. It will save your time, but without understanding the structure, that is slightly difficult. And you require so many data sets, and you need to train your model with different type of designs to have a prediction. That probably we be like a lot of data sets. It's not for a single design then. So coming to the FSS part, so now after getting the successful result of this design, we started with, we currently are working on this FSS structure. So I'll just have certain basic structures here. So maximum frequency was around 12 gigahertz. So the lambda by 2 distance was around 12.5 mm that we calculated. And we are doing for a total number of units is of 9. That's it. We are not increasing it right now. So these are the basic structures that we are actually working upon. Is my PPT visible? Is the PPT visible?
Yeah,
Yeah,
it
it's
is there.
visible.
Just a second. So the introduction of FSS in this design was mainly for the gain. I am not claiming increment in bandwidth, because we are not doing it for that. We just started it with the intention of increasing the gain, and basically gain increment as in that is a byproduct. It is actually increasing the directivity of our radiation pattern, basically, so that the efficiency is also increased, and the byproduct is that we are getting is the gain is increased. So I have only shown the 4 structures here, and where it is placed in the DRA. So this is the DRA, this DRA, and we are placing it above. Now here again a foam structure is utilized as an air gap. So this distance of this air gap, now again from the calculation we have found out that this distance should be around 12 mm from the ground plane. The FSS structure should have a distance of 12 mm from the ground plane. But for the fine tuning, like if I want from suppose 11.8 to 12.2, here I can apply ML. This is the window. where I can apply ML, and instead of doing the parametric analysis on CST, we can do it here, right? So this is the place where you can apply ML and reduce your what we can say, the time required for the computing time required for doing the parametric analysis. So these are the some of the results. So FSS for different structure, FSS 1, 2, 3. Now I did not come to the cross one directly. Of course, we had the square one, and then the next iteration we did it the square. Here I'm showing only the square. Sorry, only the cross. And we are also working on the other iterations as well. This is a kind of a fractal FSS. So the unit cell design is the mathematics behind it, but the distance at which it will be placed from our DRA, that definitely can have the ML part. The design, when we are not the unit cell design, if we are taking or bringing some fine tuning which is not having the mathematics behind it, which is not calculated mathematically, like fractal cuts are calculated mathematically, but if you are not calculating it mathematically, there you can definitely use the ML and bring the FSS structure into picture. Now here in this case, this FSS structures are kind of we are having as a LC circuit, as a series LC circuit here. So it is actually working as a band stop filter. So the band stop that we are using is from 6 to 12 gigahertz. We can also have it as a band pass filter. So depending on the design or the requirement. So because of it, these FSS structure are not contributing too much to the bandwidth enhancement. We are just maintaining the bandwidth above 65, 66%, and also the actual ratio above the 66.7% that we have claimed in the previous design, which is already published. So here we are only utilizing for the gain enhancement. So if we see all the antennas at a glance with FSS, without FSS, you can see that the first design that I have discussed, it was having a gain of 5.52, and by rotation and changing the DGS, we were able to have the design to gain as 8.7, and by introducing subsequent FSS structures, we are able to get the gain about 10 dBi also. So these are very basic structures, and we are still working on it. So here I have not shown all the structures that we are receiving, but we are able to get a gain around 15 dBi as well. But it is at a preliminary stage and not very well versed to discuss it at this point, because we need to have the equivalent circuit and everything here. If you see the percentage bandwidth and the actual ratio bandwidth, the designs are just maintaining it. And because of the directionality, the efficiency is increasing. So with the DRA, we can have a lot of designs. We can play with it. We can do a lot of work in DRA. There is a lot of challenge and a research opportunity in the field of dielectric resonator antennas. With different feeds of dielectric resonator antenna you can explore. And FSS structure, if you go and find, there are very few papers in this domain. Also, this FSS structure can work in MIMO as well. Like if I draw it here, the MIMO structure that I was having, I can have a shield in between as a FSS structure. There also we can use these FSS structures for increasing, for having a very low for increasing the isolation and all those things. So this is a very challenging field. You can use FSS and design the DRA as a filter as well. People are using as an absorber, using it as an absorber. You can use it as a filter. So this is a very you can say a field or a research domain. If we are having any PhD scholars here who are still working out, or we are trying to analyze, so DRA coupled with FSS is having a lot of opportunities and applications which can be explored, and then definitely ML will come later on. So I have tried to explain you ML so that people are not wary of using ML. But the only word of caution for you for using any algorithm, machine learning or even deep learning. For deep learning methodologies, what deep learning methodologies are doing, like I have shown you different parameters like MAE, MSE, and there are higher parameters as well. That is RMSE, that is root mean square error, or mean absolute percentage error, MAPE. These are the parameters which are each single parameters are utilized in deep learning to reduce or to enhance the feature or to enhance these values. So the deep learning will be using a algorithm which will improve the value of RMSE, or it will improve the value of MAP, that is mean absolute percentage error. Improve it as in reduce it. I'm improve the values as in reduce the errors. So that those are the deep learning algorithms that can be also used. But again, the deep learning algorithm and the ML algorithms will be useful if structurally we understand our antenna, we understand how the basic antenna works, and later on we can enhance its working by applying machine learning algorithm. So that's it from my side. Thank you. Anyone can connect with me on LinkedIn, as well as you can have my email so that we can work together in future probably. So thank you very much. If anyone is having any questions, we can discuss that.
Thank you so much, ma'am, for this wonderful lecture.
Thank you. Thank you for giving me the opportunity to discuss this work.
Ma'am, there are some query in the chat box.
Okay.
I just read this.
Sure.
Vikram, wait a minute. First of all, let that participant Hemant Kumar Vashne to be unmute. Let him ask his question directly.
Hello, good morning, ma'am.
Yes.
Yes, good morning.
Actually, ma'am, I have one question.
Yes.
Actually, ma'am, just we are using the machine learning, but in CST, either HFS, already some previous algorithm like PSO, GA algorithm already exist. What is the
Right.
main difference?
Sorry, main difference between?
Just we are using the machine learning and GA, either PSO
Right.
algorithm.
Right. You can use any algorithm. See, again, I am repeating it. The algorithm part, please do not stress when we are working on antennas. Understand your design. That is what I said. I am using the machine learning algorithms like gradient boosting, which are actually the main things that are actually currently working in ML, but it is not working for my model. You can use any model which is working for your design. So first understand your antenna perfectly. The difference in understanding the ML algorithm, you can concentrate it based on the design and the expectation of your design, not otherwise. If you
Then,
see, if you go and see anything, if you Google search or anything, here I am claiming that random forest is giving me best results. But
but
random forest is very basic algorithm. It probably anyone know a video you will get where or any material you will get that gradient boosting is or XG boosting or KNN is giving you lesser results than random forest. But here I am getting it because in my requirement that is important. So whatever you are using, techniques are that is I am again stressing. You can use any technique. Understand your model and take out the parametric analysis part of it, and then you apply any technique. You can use the deep learning methods also.
okay, ma'am, main difference between deep learning method and simple machine learning.
Machine learning, see, machine learning is like verification part that we have used it. The deep learning, what it will do by the with the word the parameters that I am using. See, I'll go back again. Right now, if you heard me, my parting words were that only about the deep learning. These are the parameters that are to score MSc, MAE.
Yes,
Deep
ma'am.
learning, what it will do? It will take one of the parameter. Now these are very normal or the basic parameters. I already told you RMSE, that is root mean square error, or
Yes,
MAP,
ma'am.
that is,
Mean square error.
yeah, mean square percentage
Mm,
error,
yes.
right? So these I can select one of them. I'll select RMSE and I'll work my deep learning algorithm only to reduce the error of by using only on I'll work on RMSE. That will be my one part. That will be only I'll concentrate on or I will just concentrate on improving my R2 score. That is nothing but deep learning. In machine learning, what we are doing, we are calculating many parameters and we are trying to analyze. This is the verification part. Again and again, I'm repeating, I'm verifying it. The prediction model, for the prediction model, you definitely can go to the deep learning part, 100%. But there, the lacuna is the parameters, the number of parameters, if you increase, then your computational time there also it will increase. And the power that you are saving here in antenna, probably that will be required to work upon. Any AI algorithm or anything that you are using, it will also require that much amount of power. So we as the antenna engineers, we need to understand where we need to use it. Otherwise, sustainability will not come into picture.
Okay. If just you are talking about the 1 point lakh data set is required in using the CST, but in CST it will take a more time. For 1 point lakh data, it will require 1 month approx.
So you see, any for training any data, you'll require the data sets,
Yes, ma'am.
right? We first you need to understand or train your model. So from where we will get the data? We will get the
Me,
data from where we are what we are working upon already. So while you are working or while you are simulating, that time only you just fetch the data. Why you need to do it again and again?
okay, but when we will go for parametric analysis, so
Hmm.
then is there any need the how much exactly data is required? Suppose when we are using the factorial method and other method
Right, you
for
can
data.
use those methods, but for curve fitting, here in our case we have done curve fitting. So for curve fitting, the data beyond 1 lakh, at least 1 lakh, be required. For the
Okay,
pointers, like for the parameters like gain and axial ratio, where we have these points, like I told you, we want some points here and there, and then we connect those points. There, the data sets can be reduced.
yes,
But
for
for the
gain and
curve
actually.
fitting, yes, for the curve fitting, you require minimum 1 lakh of data. We have not worked on a data set below 1.5. Rather, we are increasing that data. Then only it will be able to predict the things properly. Otherwise, it will not predict it.
Okay,
In my previous prediction, if you have heard it here, when I'm predicting, I'm not getting the gain and AR values perfectly. The prediction is only for the S11.
okay,
So why that is happening? Because the S11 here that the model I have used for training, it was having a data set of around 1.5 lakhs. But it was not the case with gain and axial ratio.
okay. Um, just for testing, we are using the data 80 by 20 ratio, 80 for training, 20 by testing, either 90 for training, 10 by testing.
Right,
So
80-20.
what is the main reason? Why we are using only 80-20, not 90-10 and other 90 70-30? Is
It
there any rule?
depends. There is no rule as such. In my case, it was 80-20. Why? Because see, I have used the testing data for the values which I have measured already. Means it was around this 6.4 to 6.5, 6.3 to 6.5 or 6.6 gigahertz. This was my testing data. So the test also that you will be performing, that for verification you need to know the results, or you need to know where it will go before having the prediction model. How you will test your if you have already performed the ML, Do you have any other methodology? But it will be a nice thing for me to also know how you will test it, whether is proper or not. Now, suppose you are designing it for a narrow bandwidth. This is not a narrow bandwidth. This is a wide bandwidth type of
Wide band.
bandwidth, right? If you are designing it for a narrow bandwidth, your bandwidth is suppose only 3%, 2%. So that time you do not require a data set of 20% to test. You can it will work on 10% also.
Okay,
The
okay. It
scores
depends on
will
the.
change. The parameters or the scores will change accordingly. So that is what again and again I'm stressing it. First, understand your design completely. Then only you can have a ML on it. You cannot have ML directly just randomly because I want to have a machine learning algorithm and deep learning algorithm. There is no point. Understand your design, your requirement. You work upon that. And for the parametric analysis, for predicting it in future, see first parametric analysis that you are doing, that you have to do it. Right? Then only it will be able to predict how the changes or where the changes needs to be done for a design that you don't know. But the basics you will have to work upon. That is
By
what
using
I'm saying. Yes, that is what I'm saying. You cannot just go on having a machine learning algorithm, deep learning algorithm without understanding your antenna or your parameters. You can
Okay.
you must be having that experience with ChatGPT and Gemini also. You give the prompt. We call it prompt engineering. You give the prompt, but it is not necessary. It will the answers are very elaborative. But if you go on reading it, it is not necessary that it will give you according to what you require. Because if you are not having the understanding and you just have the if you just copy paste the answers from any AI tool, 100% the person who is knowledgeable, he will understand that this is not you or this is not your understanding. The same with the case with our antenna also. Unless and until you understand it properly, there is no point in having ML algorithm. Understand it first.
Okay, okay. At least some reviewer ask if you are using the machine learning, you will take the lot of time for the training data set, and some algorithm already exists in software like a
Agreed,
GPSO and
agreed,
GA.
100% agreed. But this that what we have developed, that was for our basically you can call it as a consult. It was a part of a consultancy work. So it was as per the requirement of our client. You can call it. He did not want 72% of bandwidth. So my antenna is giving 72% bandwidth. Accordingly, my cost has increased. Right? If it is high performing antenna, he required only for probably 40%, 50%. So for that same type of antenna, I can do parametric analysis and just reduce the values or reduce the info. For such type of a thing, your ML will be utilized now.
Yes,
am
ma'am.
already having a predicted model. I'll just do some computation. I have already trained it. There, my research group does not have to again have 5-6 days to just do that. There, the machine learning algorithm and there the part will come. We are thinking only from the perspective of designing it on the CST. 100% you have to design it on CST or HFSS or any other software or anything that you are using. 100% you have to do it. But if I'm having an antenna ready with me, I'm having a 72% bandwidth overlap, AR bandwidth and 10 dB bandwidth antenna ready with me. I am claiming it that you can purchase it from me from suppose X number of money. I am having a person who is not having that much of requirement. And he'll probably pay me less also because his requirement is not that much. So I'll waste again that much energy, 5 days, 6 days to give him that requirement. Rather, I'm having a predicted model ready. I'll just compute how much should be my DGS values, and I'll give him within a day. There you can use it. That is what I'm saying. You need to have understand why you are utilizing it. It is your question is 100% valid. It is not necessary that everyone will apply ML. Understand the requirement, whether it is necessary or not. then only it is useful to apply ML. Unnecessary without understanding the without understanding that we don't know how our antenna is working and we are applying ML. No, no, that is not advisable. Not at all advisable.
Okay, ma'am. Thank you.
Yes, thank you so much.
Vikram, now we can take other few questions for in next 5 minutes because we have other expert also.
Ma'am, next
Vikram,
question is
Yes.
how to decide which regression technique is to be implemented on which design?
So that again, I'm going back to the same answer.
no.
Right? In regression techniques that you are utilizing, if you are using is for gain or for axial ratio techniques for predicting those values, the latest techniques or the gradient boosting techniques can be utilized. But if you are using a curve fitting type of a structure like S11 or prediction, so I'll claim the for this design it was random forest that was giving me best results. So I designed my predicted models also using random forest. But for the other designs, I'm having a different type of experience based on the design. Like again, I'm saying a narrow bandwidth if I'm using, then the curve fitting portions of KNN are also giving me best results. But for the wide bandwidth or for dual bands or multi-band type of curves, I have observed for 2-3 design that random forest is giving me best results. You can have random forest, you can have a basic structure. So this claim is again subjective. It is for my design. If you take my results and try random forest for your design, probably it will not work. You need to analyze that what exactly you wanted. But for a multi-band 2-3 designs that we are working upon, a random forest is giving us good results. For narrow bandwidth, you can utilize any other type of regression techniques also.
Okay.
Dr. Ankita,
Yes,
I
sir.
have one question.
Yes,
In
sir.
your that rotated DRA model, you got a bandwidth of around 70%.
Right. So
And
that
in case,
bandwidth was not because of the rotation, sir.
no, no,
Hmm.
the bandwidth, I'm just.
Okay.
But in case of your MIMO, for that rotated portion, you are getting larger bandwidth, I think.
That we
As much,
extended up to X band. So there, that is what I told in the video also. I am not using the same DGS there.
no. But why that bandwidth was suddenly increased to, I think it was doubled almost.
No, it was not double, sir. The It was around 30% only. The bandwidth, you are getting confused with S21. I'll just start again.
S11 I'm talking.
There were two plots in it, S21 and S11.
Yeah, yeah.
So probably you must have seen the S21 part. The
No,
bandwidth is around 30-35% for the MIMO part.
no,
It's not.
the actually in that S1 plot as much I can see the line was touching the minus 10 dB line.
Just a second. It was not from 6 gigahertz, but it was from 8 to 12.
Maybe.
Just I'll show you again. The center frequency has changed for it. The center frequency
Yeah.
has changed, and this was only for 8 to 12 gigahertz.
So the bandwidth is significantly increased, I
Yeah,
think.
it is for X band. No, it has shifted, sir. It has not increased. There, the bandwidth was from 6 to 11 gigahertz, 11.2 gigahertz for
Okay.
a single band. Here, I am not getting from 6 to 8. Basically, I'm not getting anything, any significant bandwidth there. Of course, I am getting the
Yeah,
center
S21 is there,
frequency.
no issue. But
Yes. Yeah. So basically, this is from 8 to around
and
12. That
yeah,
was This one was from 6 to 11.5. Yeah. This
yeah,
It was 6 to
yeah,
11.4.
6 to 11.5.
Yes.
So in that, in Nemo case, why you are getting those ripples in S11?
This one? So that is
Yeah,
because, yes, I probably have not shown the VNA here. That is because of the air gap that is introduced in between this DRS. If you press it from above,
okay,
this you will
fine.
get it smooth. So that
Okay,
is the issue
those are
basically with the DRA.
measurement tolerances. Yeah, fine.
Yes, sir. The issue with the DRA is
Yeah,
if
yeah,
there is
it's fine.
a air gap introduced in between, you get these ripples.
Yeah, yeah, okay. Thank you.
Okay, thank you so much.
Ma'am, next query is, how can we start optimization with ML for any FSS or antenna? Please suggest.
Again,
From
for
where we can
any
start?
FSS, from where we can start, as in, okay, as are you asking in terms of learning, or you are already
Yes,
having
ma'am. In terms
a
of learning.
learning, right? So you might have any antenna that you might have developed just for the learning. Simple patch antenna also. Try to just vary, have the parametric analysis of any one parameter on it, which is not having a mathematics behind it, which is not having mathematics. This is important. So if you are having a normal patch antenna, which is having the mathematics, you are suppose introducing uh, a slot in between. Now, why you are introducing that slot? First, understand that. Then you can have that slot in like if see, show you. So you if you having a patch antenna, now this is already designed and you know its length and width. Suppose I start with I want my maxima here and I want my minima in the center. So suppose I don't want in the center for XYZ reason any application. I'll just have a slot here. Now this slot you can apply a parametric analysis for 2-3 values and get those results. And then you apply a simple algorithm. You will get any algorithm or everything is most of the things are available. Replace those with your decision tree random. These are that is why in my presentation I have shown only the basics of the algorithms. I am not going into deep learning part, and I'm not going into a very other difficult type of ML. You can take any algorithm, start with decision tree and put just the data sets with that and see whether the S11 that you are observing here with CST, is it similar to the curve fitting that you are getting with decision tree or random forest? Start with only single algorithm. Okay, and start with a if you are starting it, start with a very basic design. Don't just go to the elaborative design. Once you understand that this is not difficult. The problem is we feel that machine learning will replace our antenna design. It is not going to. Please understand, not at least in coming 5-6 years, so definitely. But what we need to as antenna designers, we need to understand the working of our antenna, and we also need to incorporate these things so that tomorrow if the technology changes, we need to understand, we need to know where is the lacuna. Otherwise, what we are doing is that we are just blindly believing that machine learning will replace our antenna designing techniques. But the computation that it will require to replace the complete antenna design community, the computational problems will be too much. It will be too high. So don't worry. You start with a basic patch antenna. Just create a slot in between. Do the parametric analysis. Have around 50,000 of data sets. You will get that. And concentrate only on S11. Don't go to the other things.
Okay, ma'am. Ma'am, last query is, please, any source book from where we can learn these coding?
Coding, I am not a coding person, let me tell you. So I'll not be able to give you any book as such. My learning is also from a lot of videos and understanding the things from the internet sources as well. If you ask me about the antenna, probably I'll be able to tell you. I am an antenna person. These are the techniques that we are applying. So
Okay.
we have also learned it through from internet as well. So
Okay.
sorry about that.
Okay, no issue, ma'am.
Okay.
I think there is no more query, ma'am.
Okay.
So
Thank you so much.
on behalf of EICT MNIT Jaipur, thank you for delivering a special talk in this FDP. We truly appreciate your time, effort, and willingness to share your experience with us, ma'am. Thank you so
Thank you
much.
so much. Thank you. Thank you for inviting me.